Okay, so we're into our second topic, right? So we're just going back through a couple of key things that you should remember from sophomore organic chemistry, right? We're assuming that you're comfortable with most of the material that you saw there. So we started with absolute configuration and drawing our chairs. And today we're going to talk about, or in this video, we're going to talk about nucleophiles and electrophiles, right? So first, just classifying them as different types of compounds with different reactivity. And second, correlating them with pK of the conjugate acid, which is going to give you an idea of how nucleophilic something is. Okay, so if I think about my nucleophiles and my electrophiles, right? Nucleophiles are inherently electron rich, right? Usually there's a lone pair of electrons that's available to donate to some electrophilic partner, right? So they usually have a free lone pair or nucleophilic electrons in general. The electrophiles, on the other hand, are typically electron poor. And a lot of times they'll have an empty p orbital or a nice weak bond that you can break by attacking with a nucleophile. So a weak bond that can be broken. Okay. So some classic examples of nucleophiles and electrophiles, right? The nucleophiles are electron rich, so things like amines, where you have a lone pair on nitrogen that's available, or even alcohols or water would be good nucleophiles. Even better, something like a Grignard reagent, right? So I've drawn methyl magnesium bromide. This is the way you typically see it drawn. Of course, you can draw it as it is drawn with a carbon-magnesium covalent bond. You can also show the ionic structure where there's a plus charge on magnesium and a full minus charge on carbon, right? Which helps you to see that this is like a carbanion, right? And so it's highly nucleophilic, very electron rich, and prone to attacking electrophiles. Similarly, our cuprates, other reagents that you saw back when you talked about conjugate addition chemistry. So these are copper reagents, right? Copper with a minus. There's a lithium plus nearby in solution. Just like our Grignard reagents, you can draw these as having the organometallic bond, so a bond between carbon and copper, the metal, or you can draw them in the ionic structure to reflect the carbon ionic character, right? So you can draw copper, H3, right? And then there would be like a lithium plus somewhere, right? So just a different way of drawing your cuprate that helps trigger the idea that these are nucleophilic because there's this pair of electrons on carbon that's available for attacking electrophiles. Right, so those are some typical examples of nucleophiles. Typical examples of electrophiles, you know, everybody's favorite, maybe, one of my favorites, H3O plus, right? Protonated water is a great electrophile to give up a proton. Alkyl iodides, where we have this really weak carbon iodine bond that's prone to breaking. So alkyl halides, particularly the iodides, are prone to attack by nucleophiles. Similarly, sulfonates, so I'll draw a tosylate. They behave a lot like the alkyl iodides because they have that weak CO bond that you can break by attacking with a nucleophile. We also have carbonyls. The pi bond is what we're going to break. Or if we want to have an empty p orbital, your carbocation, right? That would be a great electrophile. And you could trap it with a good nucleophile like water or an amine. Okay, so every time you look at an organic compound, the first thing that you should do is you should try to decide, is this a nucleophile or is this an electrophile? It is amazing how far that will actually get you. And we're going to talk in more detail about this, but use your chemical intuition. When you see a new functional group, try to decide whether it is a nucleophile or an electrophile. You should be able to do that. And then as organic chemists, we basically just mix and match, right? We take one nucleophile, we add an electrophile to it, and that gives us a reaction. That's what we're looking for. Not to foreshadow too much, but you already have a significant amount of chemical intuition where when you see a functional group, you probably have an idea of its inherent reactivity. We're going to solidify that even further using FMO theory. And so we're going to see we're going to support this with FMO theory, where we're going to identify the HOMO and LUMO of compounds. And that's going to help us decide whether the compound is nucleophilic or electrophilic. But again, as I said, you already have a lot of this built in to your chemical framework, and so you should trust it. Okay. So as we're going about looking at the inherent reactivity of these compounds, if you're ever not sure whether or not something is a good nucleophile or a good a poor nucleophile, one way that you can use to compare the reactivity of it to other nucleophiles is by looking at the pK of the conjugate acid. So comparing our nucleophiles, we're going to consider the pKa of the conjugate acid. Why does this make sense? Well, let's take a good nucleophile that we know, the Grignard. You guys know that Grignard reagents are good nucleophiles. Typically, when you take a Grignard reagent, you treat it with a ketone or an aldehyde, some carbonyl of interest. And what happens is that Grignard reagent adds to the carbonyl. Right. So we can draw arrows for this reaction. We're going to use the nucleophilic electrons in that carbon-magnesium bond. We're going to attack the carbonyl, push the electrons up onto oxygen. That makes our new carbon-carbon bond for us and generates an alkoxide somewhere nearby in solution. There's the counter ion the magnesium counterion. Okay, so Grignard reagents are nucleophiles. And all that means is they can give up a lone pair of electrons to something that's electrophilic. That's not very different from giving up a lone pair to a proton, right? So if you take a Grignard reagent and you treat it with water, what do we get? We protonate it, right? And we're going to generate the magnesium hydroxide is going to be the byproduct of that reaction. What's going on here? Arrow pushing looks really similar, right? So you take your lone pair in that nice nucleophilic bond and you pick up a proton. So being a nucleophile and being a base are quite similar, right? They're similar reactions. In this case, we're using a Bronsted acid instead of a typical electrophile in order to trap that reagent. But either way, you're giving up that lone pair of electrons to something that's going to trap it. Okay, and so typically you can correlate your nucleophilicity to the acidity, pKa, of the conjugate acid. In this case, with the Grignard, the conjugate acid is methane. If you wanted to compare the nucleophilicity of the Grignard reagent to different nucleophiles, you could look at them and compare their conjugate acids. So let's do that. And of course, in order to be able to do this, we have to remember a couple of pKa's. So it is helpful to memorize a few pKa's across the range. And a good range to consider is pKa from like, whoops. We'll put 0 right around here, -10. I'm not going to be perfectly on scale here, but whatever, we're good enough. Ooh, we're really off. Dear, oh no. All right, so I want this to be 50. So I'm going to go 0, 10, 20, 30, 40, 50. Right, so our boundary conditions for pKa's that we typically run into are somewhere in between -10 and 50. So pKa of a compound that has a pKa of around -10 would be sulfuric acid, a really strong acid. Something that has a pKa of around 50 would be an alkane. And it's a bummer that you guys aren't here with me because usually I get y'all to yell them out, and all my chem majors are great about memorizing a few pKa's. All right, so most compounds lie somewhere in between, right? They're either weaker acids than sulfuric acid or stronger acids than an alkane. Some typical ones, acetic acid, right around 5. Everybody likes water, right? Water and the alcohols like methanol all hover right around 16. Ketones, alpha protons, right, to generate enolates, those all have pKa's right around 20, depending on the substituents. And amines have pKa's right around 40. Well, 35. What am I saying? Again, depends on the substituent patterns, but something like disopropylamine is right around 36. Okay, so this kind of gives us a framework for the range of pKa's we can deal with. And so if we think about the corresponding conjugate bases for each of these acids, for sulfuric acid, it's going to be that sulfate. For our alkane, methane, it's going to be the carbanion, right? And then we can keep going, right? The amide, the enolate, hydroxide, acetate from acetic acid, right? So these are all the conjugate acids, or the conjugate bases, sorry, for the acids that I drew up above. And we can rank them, their nucleophilicity corresponds to the pK of their conjugate acid. So the most nucleophilic is going to be the carbanion, and of course the least nucleophilic is going to be the sulfate, right? This is a great stable anion, which is why sulfuric acid is such a strong anion, or such a strong acid, because the conjugate base is so stable. The carbanion, on the other hand, is really unstable, which is why the conjugate acid is such a poor acid. It's unstable, which makes it really nucleophilic. It wants to give up those electrons and give them to something else, right? And so then we think about nucleophilicity here. The scale goes that the most nucleophilic are going to be the carbanions, next the amide, next the enolate, next the alkoxide, next the acetate, and finally the sulfate, which is really not nucleophilic at all. Okay, so memorizing a few of these pK is really helpful. We're going to talk about trends, and we're going to talk about, you know, fine-tuning your intuition and predicting pKs of compounds you haven't seen before. But knowing a few key numbers along the way is really helpful. And if you're a chem major, if you're remotely interested in grad school, you should start memorizing a handful now, right? Knowing 8 pKs turns out to be super useful skill in the long term for your life. Okay, so hopefully this has given you a bit of a refresher and sounds pretty familiar. And this closes out our topic on nucleophiles and electrophiles.